we want to estimate mu. So this is the continuation from the previous video. So this is the population with mean mu and sigma. So we already know now the x bar is going to follow this nice normal curve, either based on the large sample. So if you are dealing with a large sample from the central limit theorem, x bar will follow a normal curve. Or else, if this is a nice curve, normal curve, then this is going to be a normal as well for any n. So in other words, x bar will follow this normal curve. So from the normal curve, we already know that if I want to cover 95% of this curve, all I need to look at is that I need to look at within 1.96 standard deviations of the mean. So in other words, so within mu minus 1.96 standard deviations and plus the same thing. Within that, from here to here, 95% of the curve. Okay, so in other words, as a probability statement, the probability, the area is 0.95 or 95%. So this is a inequality, and this is another inequality. This is the intersection of two inequalities. So I'm going to separate it and put them together again. Okay, so this inequality is exactly, I'm writing that here. So here this one, I'm going to put this part onto the other side. Okay, so here mu, so this plus that. The same way over here, I'm going to put this part on this side. So the x bar minus that is that. So now this inequality is exactly same as that. I did not do anything. Okay, so I'm going to put these two inequalities together back again. So the intersection for those two inequalities is going to be exactly, this says that mu has to be less than that. So which is that? Mu less than this quantity. So this says that mu got to be bigger than this quantity, bigger than that quantity, this part right there. Okay, so this exactly equivalent to that. So the probability from here to here is going to be 0.95. So in other words, if you look at carefully this thing, so we are trying to estimate this mu. We are trying to estimate mu. What we are saying here is that this unknown mu value is going to be from here to here with this chance, with 95% chance. So that's a pretty high chance. So in other words, with 95% chance, this unknown value would be within from here to here. All right. So that's the interval estimate we are going to use. Actually, we are trying to estimate mu. That is our estimate from here to here. So we can say that 95% of the time we are kind of correct. Okay. So that is our interval estimate from this value to this value. That is known as a 95% interval estimate for mu, or 95% confidence interval. These are different names. Okay, 95% confidence interval, 95% interval estimate, or sometimes some books says even a level 0.05 confidence interval. So for confidence interval, level is 0.05. Or sometimes this is a more technical word, 0.95 confidence coefficient. So in other words, 95%, if you express this one as a fraction, so it's 0.95 confidence coefficient, which is the coverage probability. Coverage probability means that 95% the coverage, okay, 0.95. So that is the confidence coefficient. So basically, if you want 90%, say for example, 90% confidence interval, all you have to do is that you should be able to tell me now what you need to do. So if you want 95, it's 1.96 standard deviations of the mean right there. So if you want 90%, all you have to do is that change this, right? 1.645, 1.645. coming out of the Z table. Okay, so all you have to do is that depending on the coverage you want, you change that table value. Okay, so that way you can get the your interval estimate. So in general, so if you want 100 times 1 minus alpha percent confidence interval, okay, so when I say 100 times 1 minus alpha percent confidence interval, I am referring to 1 minus alpha in here. Okay, 1 minus alpha. So this part is alpha over 2. This part is alpha over 2. Okay. So in other words, with this notation, so if you are looking at 95% confidence interval, alpha equal 0.05. Okay, 1 minus alpha, confidence coefficient. All right. In this case, this 1 minus alpha is 0.95 confidence coefficient. Okay, or the probability coverage. 1 minus alpha is either confidence coefficient or the coverage probability. So 100 times 1 minus alpha percent confidence level. So when you say confidence level, it's a confidence coefficient expressed as a percentage. It's that. Okay, so you can use whatever the terminology you want to use. But anyway, if you're looking for this much coverage, the interval is going to be from X bar. So see, this one is the Z table, right? So here in terms of the Z table, this is going to be Z area to the right, alpha over 2. All right. So this is going to be Z alpha over 2 to the left. Okay. So here X bar minus Z alpha over 2 sigma over square root of n, X bar plus that. The bottom line is this whole interval is centered around X bar, by the way. See the X bar minus that quantity, X bar plus that quantity. See that the point estimate minus plus. Okay. So that's the interval estimate if you want this much confidence interval. So the assumptions behind this interval is basically, now there are several assumptions. The very first assumption I made is that going from here to here. Okay, so this got to be correct. Based on that, everything is correct. Okay, so this can be correct in two ways. Either based on this initial population, if this is a normal curve, this is automatically correct. Okay, you have seen that one before. So either this must be normal or this n must be large. Okay, those are the two conditions. The very first condition. Initial population, when I say initial population, I am referring to the values, x values. Initial populations must be normal or n, which is the sample size, must be large. So that way, essentially, we are using the central limit theorem. From central limit theorem, this is correct. Okay, so that one assumption. The second assumption, see that if this is our estimate, we should be able to calculate this, right? Otherwise, that is not estimate. So once you pull our random sample, if we cannot evaluate this thing, then it is not our estimate. Okay, so either this value, see there's a problem right here. Okay, so if you know this one, then there's no problem. This value is coming from a sample average, is coming from a table. So this one, either we need to know that in advance. Okay, either sigma must be known or n must be large, n is the sample size, must be large, so that sigma can be accurately estimated by S value, sample standard deviation. What happens is that if n is getting bigger and bigger, for later you'll see that. Okay, so in general, once you have a very big sample, S is a quite good estimate for sigma. Okay, so in other words, right now I'm going to put it this way. So either sigma must be known or n must be large, so that sigma, if it is unknown, you can replace that sigma by S. All right. And the third assumption is that this got to be a random sample. Okay, always we are putting a random sample, so that way this is correct. Okay, the central limit theorem or the other way. Okay, so the third assumption is the sample got to be a random sample. So those are the three assumptions. So if these three assumptions are correct, you will have a valid answer over there when you figure out that. Okay. In the next video, I will show you how to figure out how to do a couple of examples. Okay. So, but here I need to point out one thing. So, regardless of this, always you can get an answer, because even if these assumptions are not correct, if you use the formula, you are going to get an answer, but you are going to get garbage basically. Okay, you cannot rely on your answer. Answer could be anything. So, because of that, always you need to check these assumptions whether they are correct. So again, initial populations must be normal or n must be large, either that or that. All right, so the rule of thumb is that, so as of now, you can, if you wanted to, you can say this way, n more than or 30, but later I will give you exact details behind that. Okay, so the second condition, sigma must be known. Okay, sigma must be known, or n must be large, so that way unknown sigma value you can replace by s. By the way, here, if you know the sigma value, you never replace it by s, because if you know this value, you never replace that known value by estimate. This is only an estimate for that. Okay, if you know this value, you never replace by estimate. Okay, don't do that. All right, so the sample must be a random sample. So in the next video, I will do some examples.